Hi everyone, welcome to the Black Holes and Quantum Information session. The first speaker today is going to be Julian from the University of Geneva. So Julian, please.
Okay, so first of all, let me thank the organizers to have put together this wonderful conference. It's a lot of work. Thank you for putting in that work. And thank you for inviting me to present. Yes, I'm going to give a talk on the subject of chaos, complexity, and gravity, although the first and the last of these words will be, I think, the main features of the talk. The idea really is the following, is that, we often are trying to look for physical principles that might actually be a sort of really a guiding light in formulating theories that we're interested in. In our case, let's say we're interested in theories of gravity and, of course, quantum gravity. And what I want to talk a little bit about, actually very specifically about one particular piece of work, but maybe I'll take a few minutes to give a little bit of an overview, is that in recent years, actually thinking about the idea of quantum chaos has proven to be really also, to my own mind, astonishingly fruitful in serving as such a guiding light. So why actually did we start to think about gravity in the first place in the context of quantum chaos? Well, the simplest reason that I always come up with when I think about how to explain it is that the objects that we most like to test our theories against in quantum gravity are black holes. And black holes are famously known to be thermal states, or to be, in the ADS-CFT sense, dual to thermal ensembles. As, of course, goes back to the famous works of Bekenstein-Hawking and also Gibbons-Hawking and many people in that circle. So we are supposed to think of the black hole as being basically the geometric representation of the thermal density matrix. So the density matrix in an ADS-CFT sense is literally the canonical density matrix that's associated to the black hole. So these black holes are nearly perfect thermal states. And if you have a nearly perfect thermal state in front of you, then very often it is interesting to ask how we ever got there. And so the idea of forming these states, and why do these states even exist, why do we observe them, has to do with the idea of thermalization. And thermalization is well understood to be essentially a stand-in for thinking about chaotic dynamics of the underlying microscopic system. That's why, at least as far as the black hole part of the Hilbert space of quantum gravity is concerned, it's really very fruitful to think about quantum gravity, about quantum chaos. So here is just a little tour, obviously biased on things that I have been involved in. This is not a review talk. So what does this bias? Well, in the first place, and that was, I think, the first wave of excitement, it's actually a nice physical picture that explains a multitude of bulk gravitational signatures. And so in particular, I have in mind something like ADS-CFT duality. But of course, people have, in some cases, extended it beyond those asymptotics and maybe even beyond the context of some kind of holographic duality. So one of the most famous examples is the explanation of the so-called quantum Lyapunov exponent in the out-of-time order correlator using shockwave scattering. And that, of course, goes back to Kitaev, but mostly to Schenker, Stanford, and Maldacena. Now, just a plug that recently, with my former master student, Benjamin Strittmatter, we've put a little wrinkle in this story, and we added a discussion purely in terms of Liouville conformal field theory of the phenomenon of this Lyapunov exponent in conformal field theories that are irrational and have a large central charge limit. And we found an interesting mechanism that shows how you can get an exact Lyapunov exponent by exactly solving such a theory, rather than making, let's say, an identity block approximation. Now, another thing that this buys us, or has bought us, that was already commented upon today in Shira's nice talk, is that the community, including some of us, have come up with the first well-defined example of a complexity bulk correspondence where, at least in lower dimensions, in the context of JT gravity, we have identified a notion of complexity, namely Krylov complexity, the dynamics of the system in Krylov space with a bulk geometric quantity. And so this K complexity, as actually Shearer said, I think in pretty much the same words, this K complexity, you think about how efficient is the optimal exploration of such a Hilbert space, and it turns out that quantum chaotic systems are particularly efficient in exploring Hilbert space. And that leads also to this other aspect of the story that we heard about a bit from Shearer, namely it may be interesting to think about Krylov complexity as a discriminant feature between different kinds of chaotic and different kinds of integral models. So this also is work, in particular with Adrian, who has introduced me here, with Ruud Scheer, and with Eliezer Rabinovich. Okay, so however, the thing that I would like to mostly focus on, and as I said, I want to add just a detailed addendum to an overall story that is developing, is basically to go really even further and to use quantum chaos in a specific sense as the underlying principle to formulate theories of quantum gravity. So in two-dimensional gravity, this is by now actually rather well established. It goes back to the fact that two-dimensional gravity can actually be seen as a random matrix theory, RMT, which is, of course, has a long history, but has recently come to prominence again in the context of JT gravity and asymptotically ADS spaces. So Stanford, Satz, Schenker and Stanford, and also with co-authors Alex Altman, Boris Post, Eric Valinde, and Jeremy van der Heyden. This is fairly well established, I would say, by now. Also, in particular, the connection to quantum chaos, which stands in here with random matrix theory. More recently, and I think very excitingly, some of these ideas have been pushed forward in one higher dimension, namely the case of three-dimensional gravity, where we proposed a random matrix tensor ensemble. So for gravity, I call it a random tensor theory. So, which was proposed in a paper with Belin, De Boer, Jeffress, Nayak, and myself. And a recent very interesting follow-up by Dan Jeffress with collaborators, so Gabriel Wong and Lisa Rosenberg. So there was already a review talk by Jan about the general ideas. I would like to give more physics intuition. And in doing so, I would like to take the opportunity also to talk about forthcoming work with Pietro Pelliconi, who is a graduating PhD student in my group, and if you have a position, you should definitely hire him, and Herman Valinde, who you should also definitely hire, but you probably don't have an appropriate position. So the question is, what does the semi-classical path integral tell us about the underlying microstates? So let's talk about the physics here. So let's consider something like correlations of states that you can think of, we will show it in a second, as basically being the thermal state with a few Hawking quanta added or removed, depending on if you dagger or not dagger the operator. So we start with the thermophile double state, which is like the purification of the canonical density matrix, and we act with operators on it. It's like a sequence of Hawking emissions or absorptions. Now, that means that we want to study a class of observables in the context now of 3D gravity and 2D conformal field theory, which is basically a bunch of correlations where you have Euclidean and Lorentzian evolution. So in particular, you have Euclidean evolutions tau 1 to tau n that add up to beta 1 around the thermal circle, and in between, you have some Lorentzian excursions where you can place the operators. And for simplicity, for the sake of this talk, we can actually just focus on the two-point correlation example. It will be more manageable to explain. So let's say you go once, you go half around the thermal circle, you insert an operator, you go halfway around the thermal circle, you insert another operator. So the gravity contributions to this quantity are basically, well, this is sort of the naive contribution that you would like to write down and that we would have written down many, many years ago. Ignore for a second this E symbol here. So basically, I have a three-dimensional contribution to the semi-classical path integral, which asymptotes to a boundary that is a 2 torus with 2 operator insertions. So one for each of these O's. And obviously it's too complicated to draw the complex contour actually using these three-dimensional geometries, so I don't even try. So it's a two-punctured torus boundary, and actually one of the sources where you can find already the answer is Maldasena's classic paper about the eternal black hole, but there have been many more detailed explorations also since. And to cut a long story short, you basically can show that this quantity for large Lorentzian time separations decays with a characteristic exponent. It goes to 0. And actually, in this visionary paper by Maldacena, it was already pointed out, although I will not emphasize it so much today, but that this decay is actually in tension with unitarity. Now today, I would like to interpret this as the expectation with respect to some notion of ensemble that we will specify of this quantity. So that's the E here, but we will return to that. So now there is also a related gravity contribution, which is basically the contribution of a manifold that has two asymptotic boundaries that are two tori, each with two punctures. So in the again, this notation that I'm anticipating of the ensemble, this will be the expectation of G beta at T and G beta at S Lorentzian times. And this thing basically just visually has the square of what we computed before, and the second contribution, which is a connected two-boundary wormhole configuration. That is a little bit more arduous to compute, but it can be done. And I'm actually only giving you here a slightly approximate answer, also for lack of space. It's uninformative to put all the things here, but there will be dependence on constants and so on in here, so I've set this all to 1. So basically, it's precisely the square of what we saw before, and has, however, this other contribution, which you can write as cos to the minus 2 delta of T, cos to the minus 2 delta of S, and a cos to the minus 2 delta of the difference of these Lorentzian times. And what is interesting about this is that if you take large Lorentzian times, but you keep the separation small, then this quantity no longer decays. And the fact that this quantity no longer decays is something that we would like to expand upon. So in particular, let me comment on the physics of this. So we call this basically Brownian matryoshka. So the matryoshkas are these Russian dolls where you have like one doll inside of the other, inside of the other, inside of the other. Why did we come up with this name? Well, basically, let's compare this to the physical process of Brownian motion. So Brownian motion, you have a mesoscopic particle that is suspended in a fluid that we actually know is composed of molecules or atoms that constantly impinge on this mesoscopic particle. The equation that actually goes back to Einstein, but I think carries the name of Langevin, is basically a stochastic differential equation that gives the derivative of the velocity of this particle in terms of a viscous coefficient and a noise term that I call xi here. So what this gives rise to is precisely what is observed, namely that you have, on average, a motion that is damped, but you have an essential fluctuation that makes this thing buffet around and gives rise to this erratic behavior, which we can also call the mesoscopic behavior of this particle. And of course, famously, Einstein used this to infer the existence of atoms from mesoscopic dynamics. So in other words, we can actually look at the underlying microstructure by only looking at the mesoscopic phenomena. So how does it work? Well, here now, because we have this noise term, we can ask for quantities, the expectation with respect to the superimposed noise. And what we find is that the one-point function exponentially vanishes, as we have seen, also in the gravity example. But the two-point function, in the same large Lorentzian two-time limits, actually goes to a constant. And this constant is precisely what characterizes this noise, and is actually very valuable information about the UV of the system that is already seen by mesoscopic observations. So just to say it again, in gravity, basically, you can show that in the appropriate limits, basically, this one-point function decays exponentially with some gamma tilde that you've already seen, actually. It The 2-point function, on the other hand, saturates to a constant which we can express as e to the minus entropy of the underlying black hole, e to the minus twice the entropy of the underlying black hole. Now, why these matryoshkas? Well, that's just an observation, which is, I think, kind of cute, which is that, yes, you can take this limit where both times are large and their separation is small, and you seem to somehow get some of this UV noise, so you get closer to the requirements of unitarity. But in fact, if you just take a limit Ts goes to infinity with this separation also large, then even the 2-point function of this goes to 0. But then you can say, aha, but there's another geometry, namely one that has 4 asymptotic boundaries, which gives you a contribution, which is, if you want, the noise of the noise, which will, in the appropriate limit, not go to 0. So you correct, basically, this second nested information loss problem by a third, another moment of the quantity, and so on. So you go on, and you go more and more, zoom in on more and more details of the noise, and you will reveal more and more features of the UV of the theory. So these matryoshkas basically gives you some kind of Russian doll structure of hidden information, and the more you want to recover this information, the higher you need to go into the details of the noise. And actually, this is really quite parallel to the Brownian mesoscopic analogy. Okay, so the second comment on this very simple physical corner that I'm presenting to you is that this is also what you expect if you take seriously this recent conjecture that there is actually a boundary ensemble description in terms of this matrix tensor model that we suggested of three-dimensional gravity. So in particular, I mean, here it is super schematically. We have recently proposed a combined matrix tensor model for pure three-dimensional gravity, where essentially you integrate over the conformal dimensions and the OPE coefficients of the dual CFT with a potential that is fixed by the requirements of modular invariance and crossing, so V. And this approximate CFT then is supposed to be dual to 3D gravity, and it precisely gives rise to this mesoscopic, let's say, nested structure of correlators here. So this is very much, if you want, one physical manifestation that you see if such a structure is correct. Now, yes, so you can actually compute it. You can actually say, I now have this gravity Brownian mesoscopic prediction. Can I reproduce it if I assume that the boundary CFT is actually described by this tensor ensemble? So now the expectation of this correlation function would basically boil down to, in some OPE channel, the expectation with respect to the tensor model of the OPE coefficients. And this computation can be done, and you can show that you get, of course, as has to be the case, agreement with the first two moments, and for sure the other moments would also match if you were patient enough to actually compute them. Now, this is part of a much more general conjectured equivalence, which again I believe that Jan already talked about. So this matrix model that we wrote down, matrix tensor model, is supposed to be equivalent to 3D gravity, of course, in an appropriately enhanced sense that allows you to make sense of these multi-boundary geometries. And so here, this is in the sense of the recently formulated Virasoro TQFT of Collier, Eberhardt, and Zhang. Now, another comment that I want to make, which is of a statistical physics nature, is that this is also a structure which is very much the same as what we had referred to as a generalized eigenstate thermalization hypothesis. So this is in work with Daniel, with David Kolchmeyer, Bar, and Muhammad Sanov, and also strong echoes of some work of the Paris group of Huini and Korchan, where basically what one is saying that in a chaotic system, so back to quantum chaos, actually these correlation functions can be hypothesized to be described by the following structure. You take the matrix elements of operators and in a generically high enough eigenstate, M and N label the eigenstates, these are actually given by some smooth functions, which we can perhaps now skip, and some random matrix. But this random matrix, instead of being Gaussian, which was actually formulated in the original eigenstate thermalization hypothesis, was pointed out by these authors, actually has to, by consistency with many requirements of chaos and unitarity, satisfy itself for hierarchy of equations, and this hierarchy of equations basically can be summarized as saying that the expectation of the kth moment has to be given by a particular smooth function fk, which is strongly suppressed in entropy, but which, despite its strong separation in entropy, leaves indelible evidence on physical quantities. And here I showed you that it has to do with this underlying irreducible noise that is in correlation functions, and the noise is excitingly actually a window into the UV of the theory. So in this sense, this E here now is an expectation, for example, with respect to the ensemble generated by chaotic dynamics in this sense. Now, this leads me somewhat early to my conclusions, which is that the general idea of how to use quantum chaos to think about quantum gravity is that we have shown now in 2 and 3 dimensions that gravity can be realized as an exact ergodic phase of a maximally chaotic system. I emphasized exact, and I emphasized 2 and 3 dimensions. I am not convinced that in higher dimensions this will be true, that there will be an exact equivalence, but more than likely there will be a large range of parameters where this is an extremely useful description, and maybe we get even more than we bargained for. Now, the other thing that I illustrated, basically without giving too many details, was that chaotic dynamics drive complexity. And this in itself is something that, to me, is an interesting subject to pursue. Namely, can we find, using the set of tools, the toolkit of a quantum chaos, information theoretic discriminants of random versus pseudo-random behavior? That's something that also increasingly crops up in the context of ADS-CFT and in the context of gravity. In fact, there were interesting recent papers by the MIT group around Netta Engelhard that were essentially not talking about the background chaotic dynamics, but they were basically using statements along these lines. Now, furthermore, I have shown that assuming that the underlying principle is chaos allows you to formulate a conjecture, namely that 3-dimensional gravity can be rewritten as a novel kind of matrix tensor ensemble, which is in the most efficient way constructed as the maximum ignorance ensemble in the sense of Balian, which is consistent with the bootstrap constraints. So it's also, if you want, a statistical version of the 3D, 2D bootstrap. But the fact that you write down such a statistical version of this is, in fact, just justified by quantum chaos. That is the key element that allows it. And then I showed you that, as I said, really just wanted to use this time to give you a glimpse on some of the more physical manifestations. And you can basically show that there's a mesoscopic regime where indeed the gravity path integral gives you a description that is intermediate between the IR and the UV, meaning it is not really a full UV description, but nevertheless, if you study, as I was actually doing, the irreducible noise that is visible in correlation functions, you are forced to conclude that there are certain UV microstates that give rise to these fluctuations. And that is really in complete analogy to Einstein's deduction of the scale of atoms, of the reality of atoms, just by looking at mesoscopic observations. And it is a physical explanation of to the question that people have been asking in recent years: why is the semi-classical gravity path integral so damn clever? Why does it know about the UV? Well, it's the same principle that's at action here. So thank you for your attention, and I'm open to questions.
Thanks, Julian, for the nice talk. We have a few minutes for questions, so see one over there.
So suppose I'm looking at the two-puncture genus 2 contribution to the two-point function. Does it go to 0 at late times?
I would think so, yes. For the same reason. I mean, it doesn't go to 0 in the limit that Ts are both large, T minus S is small. But it goes to 0 in the limit that Ts are large, T minus S also large. Well, do you have a reason to think it doesn't go to 0?
No, but I just don't like wormholes. But suppose, do you think what you said is correct for any genus bigger than 1? So you have to consider topology.
Yeah. In general, those topologies, though, would be suppressed in each of the S. So I think at very late times, like truly the late time limit, this mesoscopic description actually breaks down. And then these things probably contribute at the same level. But for the regime that we looked here, they do give subleading contributions.
When you mention the theory of when you mention the theory of three-dimensional Einstein gravity as a matrix ensemble, do you specifically mention the largest C limiter?
Sorry, I read the mic cut out. Yeah, maybe you can just say it to me without the mic.
When you say the theory of three-dimensional pure gravity as a metric ensemble, did you specifically mention the largest C limit? Or you also can see the theory as a finite C?
Good. I think this should be valid in an expansion on large C.
Expansion large C, okay. Okay, I expect so. It's possible, but the finite C is not okay. It's right.
Is what?
If you consider finite C, then you cannot see ensemble. It's right.
I don't know. I mean, you can certainly see traces. But by the way, in the paper by Daniel and Gabriel and Lisa, they actually look at each of the minus C type expansions because it's around large C. But finite C, I mean, do you mean C is equal to 1 or?
Yeah, because if we go to the Witten's paper, I think they say that we have a no-go about later. But for large C, it's no violation. But for
the no-go theorem about writing down a tensor ensemble, this I'm not aware of.
Yeah. Yes, it's not. Yeah.
We'll talk about it. I'm not aware of what you're talking about.
Okay.
Are you talking about this paper by Schlenker and Witten?
Yeah, Witten.
Okay, yeah. I don't think that is actually a valid counter argument to having a tensor ensemble here.
Okay.
We can talk about it later.
If you have time,
It's a quick one, a general question. So it's about the possible connection to string theory.
Yes.
So in this inference from mesoscopic towards microscopic,
Yes.
do you see any route to inferring the existence of extended objects in the UV of the gravitational theory?
I don't see them, but that's not to say that I don't see a possibility, but I haven't thought about it. I haven't thought about like going even further and saying there have to be, of course, we would all like to sort of in the end believe that string theory will be the only consistent UV of this, and that would be one other way of trying to go there. But obviously, I actually have nothing to add of interest there right now. Thanks.
Okay, with this, let's thank the speaker again.